Welcome to this explainer. Look, if you've been paying any attention to the AI space lately, you know we are way past the era of just typing a question and crossing our fingers. Today, we're taking an organized tour of how prompt engineering has actually matured. It's evolved into a highly rigorous discipline for production-grade AI. Let's get right into it.
Let's just shatter a really common illusion right out of the gate. Getting good AI outputs, it is no longer about asking nicely. As the 2026 production manual states, it's really about context engineering. We're designing the entire context window to act as a strict bridge. It's a bridge between a probabilistic generator, the AI model itself, and your deterministic, completely predictable software systems.
Which means it's time to say goodbye to those chatty, conversational wishes. Our new baseline is the CTCO framework. That stands for context, task, constraints, and output. This is exactly how you guarantee the model knows the specific world it's operating in, what it needs to do, the rules it absolutely cannot break, and the exact shape of the data it needs to hand back to you. No more guesswork.
Here is our tour map for today. We'll cover the context engineering shift, foundational prompt structures, advanced reasoning techniques, the vocabulary specificity factor, and finally, production controls and security.
Part 1. The context engineering shift.
We literally have to stop treating the context window like a chat box. When you operate at scale, conversational prompts lead directly to over 21 distinct agent failure modes identified by researchers at EPAM. Two of my absolute favorites, ugly wish granting, where you state a wish just a bit too loosely and the agent grants it literally, kind of like a cursed genie actively trying to ruin your day. And then there's default fill slop, where the model just plugs the gaps in your vague prompt with mediocre boilerplate internet garbage. To fix this, you absolutely need a rigid API contract.
Part 2. Foundational prompt structures.
You really should always treat your prompting like a stack, flowing logically from system boundaries right down to the specific user query. First, you define the assistant's role and rules. Then, you specify the exact task. If needed, you provide a few highly targeted examples, few-shot learning. And only then do you drop in the context or documents, followed finally by the actual user query and the expected response format. This specific, intentional ordering prevents the model from losing the thread of what it's actually supposed to be doing.
So the crucial takeaway here is that you must ruthlessly separate your behavioral instructions from the user data. If you just mix your rules into the exact same paragraph as the user's input, the model is going to get confused about what's a hard rule and what's just text it needs to process. By using clear delimiters like XML tags, you create hard physical boundaries in the context window. It makes a massive difference.
Part 3. Advanced reasoning techniques. When you need to choose a reasoning technique, the path isn't always linear. Look, we all know chain of thought, asking the model to think step by step. But when tasks get complicated, we move to tree of thoughts, allowing the model to explore branching paths and actually evaluate them along the way. But what you really need to know for the 2026 production environment is that graph of thought actually outperforms both linear and tree structures for standard workloads. It allows the model to connect non-linear ideas, mimicking a much more sophisticated, human-like problem-solving process.
Part 4. The vocabulary specificity factor.
Now, intuitively, we all tend to think that using highly specific, domain-expert words is going to give us better, more accurate results. The logic goes, if we sound smart, the AI will act smart, right? Well, a really fascinating recent study on how prompt vocabulary affects domain knowledge reveals a super surprising truth. It's a complete trap.
Negative 0.89. That is a massive negative correlation. It clearly shows that using highly specific verbs actually destroys a large language model's performance in reasoning tasks. The researchers went in and systematically substituted normal words with highly specific synonyms across STEM, medicine, and law datasets, and the AI's performance actually tanked.
Which forces us to ask a really weird question, right? Why does a massive, incredibly capable model like Llama 3.1 70B suddenly fail at standard math and logic problems just because we swapped a simple verb for a highly specific, complex synonym? The research indicates that reasoning tasks fundamentally require abstraction. Overly specific action words, the verbs, disrupt the model's ability to follow a logical, generalized progression. It gets completely bogged down in the linguistic complexity of the action itself, rather than just solving the underlying logic puzzle. Now, interestingly, specific descriptive nouns are totally fine. You can use highly specific medical terminology for a disease, for example, but you really should keep the verbs simple and abstract so the model can still confidently reason its way through the core problem.
Part 5. Production controls and security.
To harden your systems, you need some rapid-fire best practices. You absolutely must define exact fallback behaviors. Ask yourself, what should the AI do when it just doesn't know the answer? You also need to mandate a strict output schema, like JSON with fixed keys. This is absolutely vital for keeping your agent from falling into what we call working memory rot. That's where the model's active runtime memory degrades over long tasks because it just loses track of its state. A strict format acts like a solid anchor.
We've also seen a massive shift in how we actually control the models. In the past, we just tweaked the temperature setting, right? Just to make the model a little more or less creative. But today, in the 2026 production environment, we rely on a parameter called reasoning effort as our primary control dial. You're now telling the model exactly how much computational effort to expend on the logic itself, rather than just randomly adjusting the unpredictability of the words it spits out.
When we look at data from the Jailbreak Radar dataset, it reveals the persistent, ongoing vulnerabilities these models face. There are incredibly high success rates for adversarial attacks like AutoDAN and GCG across various harmful categories like adult content, political activities, and unauthorized practice. Attackers are constantly, actively trying to break that interface contract we discussed earlier.
To defend against those highly sophisticated attacks, a strict instruction hierarchy is now completely mandatory. This mitigates OWASP's #1 risk for AI by ensuring the model always, without fail, prioritizes the developer's system rules over manipulative user inputs. You have to layer this with input pre-processing classifiers to catch bad intent early on, and output evaluations, like strict must-not-contain checks to ensure forbidden content literally never makes it to the user.
And token count analysis totally proves why we need these layered defenses. Attackers aren't just asking simple, tricky questions anymore. They are actively using massive, highly complex prompts with incredibly high token counts. They do this to forcefully bypass standard safety guardrails by totally overwhelming the model's context window with deep role-playing conditions and convoluted instructions.
So as we wrap up this organized tour, I want you to look at your own systems and ask yourself a really hard question. Are you truly engineering context, or are you just hoping the AI guesses what you mean? Because precision is everything. If your system was hit with a highly complex 5,000 token adversarial prompt tomorrow, would your interface contract actually hold?